Okay, action! Okay, so happy Friday, everybody. Welcome back to another edition of Chem 111A, the course that keeps on giving. It's an awesome course, though. It's a little overwhelming, I'm sure, for teacher, student alike, but it's good hardcore science course. Okay, so we'll finish chapter 11 today. We went through all the main intermolecular forces. I still have to talk about ion dipole for a moment. We'll go through some properties of liquids. These are sort of little minor topics, but they're still kind of fun to go through. We'll do some calculations of phase change. We'll do the Clausius-Clapeyron equation, which is an equation used to calculate the heat of vaporization of compounds. Supercritical fluids and phase diagrams. I'll have to go through. All right. So hopefully you have your chapter 11 notes. I don't have any extras on me. We left off on this example last time. We were talking about H bonding. These IMFs, okay, intermolecular forces, I think I mentioned at the very beginning of the chapter, they mentioned they affect density, they affect heat of sublimation, heat of vaporization, heat of fusion, melting points, boiling points, blah, 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 boring stuff to me. But what did excite me was the fact that it also affects solubility. I didn't write solubility on that very first slide for the chapter notes, but hopefully you have solubility written there. Because solubility is really going to be a big factor in actually in our lab today that we'll do, and also it's a big factor in what I did in industry, which is chromatography. So let me talk about solubility for a moment. So the solubility of substances in another substance depends on the concept of like dissolves like. Okay, so what does like dissolves like mean? What does that mean? Crickets. Yeah, polar dissolves in polar, non-polar dissolves in non-polar. So the concept of like dissolves like means that once you determine the polarity of a substance, you can say, well, it should dissolve in this and not so much in that. Okay, so what we usually look for is either hydrophobic or hydrophilic functional groups. And functional groups are essentially groups of atoms that allow a molecule to be polar or not polar. Polar functional groups would include hydroxyl groups, OH groups for hydrogen bonding. CHO is a functional group for aldehydes. So like one of your favorite aldehydes might be formaldehyde, used to involve dead bodies. We have carbonyl groups. I'm really not organic lingo here, so don't worry about it if you're like, what's he saying? Just know that C-double bond O is also somewhat polar. It creates a dipole moment in molecules. We've got carboxylic acids. This is a real big one for what we'll do for the biofuels experiment later. So we got carboxylic acids. Actually, I'm sorry, these are peroxides. This is carboxylic acids. But essentially, more OH bonding is what they produce. NH groups, otherwise called amines. Okay, those also hydrogen bond. So all these kinds of groups introduce polarity in compounds, larger compounds, by giving the compound hydrogen bonding capabilities with water, especially. So for hydrophobic, though, for nonpolar groups, you're basically just looking at nothing but carbon and hydrogen, or a vast majority of it. So when we talk about polarity, there's two contexts. Small molecules, in which we look at symmetry. For big molecules, larger molecules, vitamins, enzymes, proteins, coenzymes, big biomolecules, we're looking at these kinds of functional groups to define polarity, even if the molecule were symmetrical, right? We don't care about symmetry anymore when it comes to big compounds. What we're looking for is, do we have hydrophilic groups on the molecule that make it dissolve in water? And we know that water is very polar. Okay, and if we don't see those groups, then it's non-polar. So miscibility refers to do things mix. Basically, that's what miscibility means. So what happens when pentane and water are mixed? Okay, well, pentane is nonpolar, water is very polar, and so you get two layers. Okay, the two are said to be immiscible. You'll see two layers form. All Okay, what's happening here is the water molecules, they love each other. Okay, like it's like a big family. Anyone from a tight-knit family? Anybody here? Like, you're like, no, we don't like our siblings. No. Hate our siblings, hate our parents, hate our aunts and uncles. We hate everybody, right? No. Or it could be like, like our family. My family's pretty tight-knit. My wife comes from a really tight-knit family. So they always talk to each other all the time. We're always on the phone talking, Sometimes sometimes family members can love each other to death, literally, right? It kind of feels almost suffocated. Anyway, but it's a good thing. So water molecules, by analogy, they're a big, happy family. They're really tight-knit, okay? They never want to leave each other, okay? And because of that, the attractions between them are so strong that when you mix these two solvents, the pentane is literally pushed out. It's like water saying, we don't like you, we're going to literally push you, squeeze you out with our hydrogen bonding and not let you in. Okay, these molecules of pentane cannot break these hydrogen bonds to infiltrate that layer. Okay, and so as a result, you get two layers. And of course, the pentane molecules, they're all right with that. And the reason why is because they get to do what kind of IMF, what kind of intermolecular force do they get to do? So these are non-polar molecules. What's the only dispersion forces, right? So they're okay. So we got dispersion forces going on up here, and we got hydrogen bonding going on down here as the primary, as the prominent attractive forces between molecules. So that's just going on. So, so water could infiltrate, but again, water doesn't want to leave its brethren. Okay. So we get two layers. Now, if you do just look at polar solvents in general, ethyl alcohol is polar. Here's a hydrogen bonding interaction between ethanol molecules, but they can also mix with water. Okay, here's dichloromethane. It's a polar molecule that has a dipole moment. It can't hydrogen bond, but it can mix with water to a certain extent with its dipole aligning up with the dipole moment of water. Right, you could have some mixing there. Of course, you got water itself. If I asked you which one would probably be more soluble in water, would it be ethanol or dichloromethane? Which one of these two would you want to mix with water, do you think? So what force could this do with water? Can it hydrogen bond with water? Does this have an OH, NH, or FH bond in it? It doesn't, right? So all this can do is say, well, I'm going to line my dipole moment, which as it's drawn right here is pointing downward, and I can take this water and move it underneath here and have the head to tail dog sniffing dog scenario with dipole forces. Or I can take ethanol and mix it with water, and ethanol can hydrogen bond with water because it also has an OH bond in it. So I would say ethanol would probably be more soluble in water than dichloromethane would be. And the reason why is because this is more like water. It can hydrogen bond like water can. Like dissolves like. Okay. So when you're matching the type of attractive forces, you're increasing the solubility of two salts or two substances. Does that make sense? I hope. Like dissolves like. Here's some nonpolar solvents. You got the N-hexane. The N just refers to the fact that the carbons are in one linear chain. Here's toluene. I used to work with this all the time. Kind of nasty stuff, carcinogenic. I hope it doesn't come back to bite me years from now. But so here's toluene, nonpolar. Here's carbon tetrachloride, also nasty stuff. Nonpolar. See, this is nonpolar because of the symmetry. It's a smaller molecule. This is nonpolar. It's kind of symmetrical, but it's got just all carbon and hydrogen, right? This isn't necessarily symmetrical, right? It's got a CH3 group on the top there where it doesn't have any on the bottom, but it's also considered nonpolar because it's all carbon and hydrogen. Right? So bigger molecules, we're looking at hydrophilic groups that make it polar, or if there's a lack thereof, it's not polar. Okay. So these would be more soluble with that pentane that I mentioned earlier. Choose the substance in each pair that is more soluble in water. Methanol or this? So would methanol be more soluble in water, or would this be more soluble in water? This guy, right? Because it can hydrogen bond with water. It shares a more common attractive force, dominant-wise, with water. Okay, so methanol can mix with water a little bit better. What about these two? Which would mix better with water? Yeah, second one, right? This is just going to be a second layer that built on top. It won't mix with water. This, to a certain extent, will mix with water. What attractive force will this use to mix with water? Dipole. Remember, everything has dispersion forces no matter what. Only polar molecules have dipole forces that it can do. Only OH, FH, and NH bonds in a molecule make it hydrogen bond. This doesn't have an FH, OH, or NH bond in it, but it does have a dipole moment. And water, even though its primary preference is hydrogen bonding, water also has a dipole moment that it can do dipole forces with this. Okay. So if I were to draw this, it would be, here's my chlorine. Dipole moment points upwards because the chlorine is more electronegative. And here's my water. Right, there's a dipole attraction. Don't forget, dogs sniffing dogs. Okay. You're like, we'll never forget that. We're traumatized for life. Mm-hmm. Okay, so this is how this will mix with water. But it's not as good as, say, methanol. Methanol can take its OH group here, you know, take, here's the CH3, you know, it can kind of come off to the side, you know, and bond it with water. So don't forget, H bonding is stronger than dipole forces because it's a numbers game, you know, and it's the, I think I talked about this last time, the side checkout's less offensive to people, so it's easier to do, you know, and things that are less offensive are actually more attractive. Okay, so any questions on solubility, miscibility?
You keep saying that the big compounds are looking for hydrophilic groups?
Right. Hydrophilic, I should have mentioned this. Hydrophilic just means water loving. Water loving, yeah. And hydrophobic means not water loving. Okay, fear of water, hydrophobic. When people have a phobia of something, they're afraid of it, right? So, same idea, hydrophobic. Okay, non-water loving, whereas hydrophilic means water loving. Okay. Yeah, I asked you the term because sometimes I'm speaking the language and it's already in my own mind, but it's not necessarily coming out as English. Okay, so last attractive force I want to talk about is something called ion dipole attractions. When ionic compounds dissolve in water, okay, you get, for example, if we dissolve sodium chloride in water, the chloride ion is surrounded by water molecules, and the sodium ion also gets quote-unquote solvated by water molecules. What solvation means is it just means the water molecules surround the ions, okay, and they align their dipole moments with the charges that are in the ions. So there's a key observation that I want you to make in this picture. What's the difference between this picture and this picture? Does anyone see a main difference? What are the water molecules doing that are different in both pictures? The direction of the waters should appear different to you, right? So here's water, HOH. The positive end of the dipole moment of the water, which points this way to the negative end, the positive end lines itself up with the negative end of the chloride, or the negative atom, which is chloride. Okay, in this case, you have sodium cation. Now the oxygen is pointing towards the cation, right? Because again, the negatives are lining up with the positive. So just like all the other intermolecular forces, this is a Coulomb's law situation, right? Opposite charges are attracting. The main difference between these is that they're even stronger than hydrogen bonding. How are they stronger than hydrogen bonding? Well, the key feature of this, I want you to write this down. This is a partial charge on the dipole moment attracting to an absolute charge of the ion. So this is an absolute charge, partial charge interaction. That's a key feature of this attractive force versus H bonding, dipole-dipole, and dispersion, which are all partial charge interactions. So look at the negative sign here. This literally comes from the fact that we have an extra electron on that chloride. It's an absolute negative charge. So the key word there is absolute negative charge. Absolute meaning literally we have an extra electron, or in the case of sodium, we have one missing electron. So now we have an excess of charge. Whereas with this delta sign, okay, that just means that there's equal numbers of electrons and protons still. It's just that the electrons are distributed in their density towards one end of the molecule. Okay, so that's what we've been talking about this whole time, this idea of partial charge. You know, we've got electrons that, as a cloud of locations, most probable locations the electrons occupy, they want to move towards one end of the molecule. But there's still an equal number of protons and electrons in the molecule. Okay, so in water's not an ion, okay, it's just a polar covalent compound. But chloride ion is an ion in absolute terms. It's got an extra electron there. And so as a result, these partial charges on the water are attracted even more to that absolute charge of an ion. This is stronger than hydrogen bonding. In hydrogen bonding, okay, this is just partial negative, partial positive. Right? They're both partials. Both partials. But in this picture, no partial sign there. It's just a flat out plus or minus. No delta sign. Right, and that's the key feature of this particular intermolecular force. Am I making any sense whatsoever? You can nod your head and tell me yes, even though I'm not. But, so these forces are even stronger than dispersion, dipole-dipole, and H bonding because of this absolute charge attraction.
So it's an absolute charge attracting partial charge.
From the water.
Versus just partial charge.
Right, exactly. Right. What does partial mean? What does that mean to you? Well, for a moment would be like dispersion, right? But for polar compounds, like with dipole moments and hydrogen bonding, the partial charges are permanently there. But the word partial, again, you should reason it in your mind as electrons and protons are equal in number, just that electrons are kind of shifted towards one end of the molecule. All right, and there's a little bit of extra charge at one end because of that. Right, but I still have a neutral compound overall. Whereas with an ion, I literally have one missing electron or one extra electron. Right. So the word partial should mean to you, it should mean electrons equal in number of protons, but just shifted in the molecule. So I use these words, but they should mean something to you. All right. So these are one of my favorite forces because they have to do with drug chemistry a little bit. Okay. So here's the diagram just showing the pecking order of the IMFs. So dispersion weakest, dipole-dipole a little bit stronger, hydrogen bonding a little bit stronger, ion-dipole even stronger still. Okay. The only other intermolecular force that's even stronger is flat-out ionic bonding. Cation bonded to an anion. We'll talk about that in chapter 12. But that's the pecking order of the intermolecular forces. So why is this stuff important? So I kind of feel like I'm a little bit of a drug dealer today. Does anyone want any drugs? They're over the counter, I promise. Actually, a couple of these are prescription, but yeah, I got oxycodone. No, that's a prescription. Just kidding. So anyone want a box? I'm going to have you, it's an exercise just to illustrate the importance of ion dipole. Like I talk about it, but what's the importance? You want this? I know you want some. You got some basically Benadryl. Take that. Allergies, anybody got them? Alright. Anyone congested? I got some Zycam here. Oh, I almost felt like Tom Brady for a moment. Let's see, anybody got a cough they gotta get rid of? Alright. Let's see, anybody want some Sudafed? It's children's though, it's not good. This is the box. The boxes don't fly. Alright. Anybody, I forget what this is for now. It's, oh, I think this is like, yeah, I won't say what it's for. Alright. Alright, anybody have a bacterial infection? Here's one for an antibiotic. Anybody? What? Richard wants an antibiotic. So, on each of these boxes / bottles, there's an active ingredient on the bottle. And on some of these I put a little sticky note pointing to the name. I'm going to have everybody read the name, and hopefully you will hear a commonality in all the names. Okay, so what's your name?
It is diphenhydramine.
Diphenhydramine.
Oh, hydramine, hydrochloric acid.
Hydrochloric acid, or hydrochloric.
Hydrochloric.
Yeah. Alright, so, and then Kate, you need to read yours.
Dextromethorphan, HBr.
HBr, which would be like hydrobromide versus hydrochloride, I guess, okay. And Yoshi had
oxymethyl hydrochloride.
oxymetacholine hydrochloride, okay. And who else had one? Brittany?
Pseudoephedrine hydrochloride.
Pseudoephedrine hydrochloride.
Tamsulosin hydrochloride.
Yeah, tamsulosin hydrochloride. Any?
Cetirizine hydrochloride.
Cetirizine hydrochloride, yeah. Is that everybody, or did I miss anybody? What's the, do you hear commonality in the names? Oh wait, there's Richard, I forgot.
Is it this one? No.
Yeah, it starts with a C.
The ciprofloxacin, HCl.
Right, ciprofloxacin,
There
HCl.
you go.
Yeah, it's like rolling off the tongue. It's like speaking Spanish, you gotta have a rolling R almost in some ways. Yeah, Cipro is a really nasty antibiotic. I had a bacterial infection that didn't feel like going away, so they put me on the really nasty stuff. They only prescribe that now if it's like a last resort, it's that nasty. Apparently it's been linked to like ruptured tendons and stuff like that. So maybe like 10 years from now you'll see me all weird and stuff. But anyway, so clearly there's a commonality in the names of what is it? Hydrochloride, right, or HBr, HCl. You see these names in them, right? Here's the importance of ion dipole forces in medicinal chemistry. Okay. Okay, so which compound would be would it be ammonium, or ammonia would be more soluble in water? What force would this molecule do in water, ammonia? What would it do with water if you mix it in there? Yeah, so like here's water, right? You got your hydrogen bonding here, right? Right, you got that kind of stuff. Here's another hydrogen bond there you can do. So H bonding, what would be the kind of force that this molecule could do to water? Ion dipole. Okay, so we know now that the positive charge comes from the fact that the formal charge on this nitrogen is a +1. Right, group number 5 for nitrogen minus the 4 bonds gives you a +1. Like 5 minus 4 gives you +1 for the formal charge. Here's what water is going to do when it comes into contact that ammonium, okay? The ammonium is gonna have an absolute positive and a partial negative for the dipole moment. Okay, so which one's more soluble? Is it gonna be ammonia or ammonium that's more soluble in water? Ammonium, okay. NH4 plus is more soluble because ion dipole forces are greater than H bonding, right? They're stronger forces. Here's what happens in medicinal chemistry. Most of the compounds, certainly the active ingredients in the drugs I threw out at you right now, they're all amines. They're all ammonia type compounds. Okay? If I add HCl to this, right? So if I add hydrogen chloride, or in other words, hydrochloric acid, to ammonia, okay, I'm going to get ammonium, and also I'm going to get chloride ion. So the name hydrochloride in the drug name comes from the fact that they acidified the drug into a ammonium chloride salt, hydrochloride. Right, that's where that term comes from. So why would they acidify a drug? Well, most drugs are amines, okay? In other words, they're bases. Okay, so you might remember way back, chapter 4-ish, way back in the day, we had acids and bases, right? We were talking about three main kinds of chemistry, right? Precipitation, acid-base, redox. For acid-base chemistry, how do we identify a weak base? We identify it by having a nitrogen group with either 0 hydrogens or up to 3 hydrogens. Ammonia is a base. You might remember that. Does that ring a bell? Ammonia is a base. Throw it in with an acid, you get ammonium chloride for the product. All of those drugs that you have, okay, are ammonium salts of the drug. Why would they want to do that? Why would they want to acidify drugs? Well, what's more soluble? The ammonium chloride salt form of the drug, or the free base, as they call it, form of the drug? Ammonium chloride form is more soluble, right? Why do they want to make the drug more soluble? What are we made out of? What is the vast percentage of our body made? What does it come from? Water. We are aqueous organisms, okay? So because of that, they acidify drugs into ammonium chloride salts to make it more soluble in us so that we can metabolize it better. And as you saw with all these different drug names, it's all over the place, right? It's the world around you, but a lot of people don't pay attention to that stuff because they just don't know, right? But anyway, ion dipole forces, one of my favorite forces to talk about because I'm seeing this medicinal chemistry right in front of me, but nobody really talks about it, you know, so I'm talking about it. It's going to be cool. So why is this important? Medicinal chemistry. Here's one really good example of why it's important. All right. All right, any questions? So to summarize the intermolecular forces, okay, dispersion is the weakest, dipole is the next strongest, hydrogen bonding next strongest, ion dipole even the strongest still. The last one will be ionic bonding, that is going to be next.